When you type a prompt into a standard AI coding assistant, it travels down a linear pipeline. The model receives the text, generates a response, and passes it back. But as context grows and complexity increases, this single-threaded architecture inevitably maxes out its capacity and fractures under the pressure. The breakdown occurs at three precise stress points. First, context windows hit their token limits, forcing the system to arbitrarily drop critical project constraints. Second, API costs spike exponentially as massive payloads are sent back and forth for minor edits. Third, parallel autonomous agents lose alignment, compounding goal drift until the output no longer matches the original specification. Ruflo, formerly known as Cloudflow, operates differently. It is an agent orchestration platform designed to manage these exact failure states. An orchestration platform functions as a compiler and runtime environment. It sits entirely between your local IDE and the foundational LLM, intercepting and managing every piece of data before the language model ever sees it. We are going to deconstruct Ruflo version 3.5's internal architecture to see exactly how it physically bypasses standard LLM limitations. We will examine four specific technical pillars: WebAssembly routing kernels, Byzantine fault-tolerant swarm coordination, custom binary vector storage formats, and continuous learning loops. Scaling AI engineering requires abandoning simple API wrappers. True autonomous development demands a rigorous distributed operating system to manage the underlying intelligence. The hook system intercepts the developer's input at the source, preventing direct, unmanaged access to external LLM APIs. Once intercepted, a mixture of experts classifier evaluates the task. It scores the request's complexity using Q-learning algorithms to determine exactly how much computational power is required. Many daily coding tasks are structurally simple. Converting a variable to a constant, adding type annotations, or stripping out console logs requires zero deep reasoning. The router isolates these simple code transforms and diverts them to the Agent Booster subsystem. Agent Booster uses WebAssembly, or WASM, and abstract syntax tree analysis to execute the task entirely locally. By handling these transforms through WebAssembly, the execution achieves sub-millisecond resolution at zero cost, requiring exactly zero calls to an external LLM API. Contrast this with heavy workloads, like a comprehensive security audit across a massive codebase, which requires deep architectural understanding. The Mixture of Experts router evaluates these heavier tasks and directs them to appropriately sized models, routing medium edits to Claude Haiku or Sonnet, while reserving complex architectural reasoning for Opus. This intelligent three-tier routing structurally preserves your available context window by aggressively filtering out trivial noise before it consumes your token quota. Execution latency and runaway API costs are solved by starving the expensive LLM of simple tasks and relying on local WASM kernels to do the manual labor. When tasks are complex enough to require multiple specialized agents working in parallel, the system introduces a new vulnerability, multi-agent goal drift, where autonomous agents diverge from the core architectural specification. Ruflo solves this by treating AI agents strictly as nodes in a distributed computing network. This diagram outlines the hive mind topology. A central strategic queen node directs specialized worker nodes, coders, testers, architects, managing their execution on strict parameters. If a single worker produces anomalous code that conflicts with the established architecture, the system forces alignment without human intervention. The Queen node resolves this using Byzantine fault tolerance, a consensus protocol in distributed networking. The requirement is an F less than n/3 faulty node ratio. The healthy nodes vote, achieve a supermajority, and override the anomalous output to restore the swarm state. When strict, sequential execution is prioritized over democratic voting, the system pivots to the Raft consensus protocol for rigid leader-based log replication. Goal drift is eliminated by enforcing strict mathematical consensus protocols that hold individual agents accountable to the entire swarm. Sustaining context and enforcing specifications across a massive agent swarm requires an entirely distinct memory layer. Local AI memory traditionally relies on large SQL.js dependencies. Loading an 18-megabyte WASM blob creates a massive cold start bottleneck, dragging down the speed of operations. This diagram breaks down Ruflo's engineered replacement, the RVF, or Ru vector format, binary layout. It consists of a 4-byte magic header, adjacent metadata section, and packed binary entries. RVF is written in pure TypeScript with 0 external dependencies. This lightweight footprint forces system cold starts down to under 50 milliseconds. Integrated directly into this binary format is HNSW, Hierarchical Navigable Small World Indexing. HNSW graphs allow the memory substrate to perform sub-millisecond semantic search retrieval directly within the Node.js runtime environment, entirely eliminating external API calls for context lookups. For terabyte-scale enterprise swarms, the local RVF format synchronizes with the RuVector PostgreSQL bridge. Ruflo leverages the PG vector extension to execute heavy mathematical operations like multi-head attention mechanisms and graph neural networks directly inside the SQL database layer. Infinite context is achieved by treating conversation memory as a highly indexed local binary database, rather than a rolling volatile text window. The final architectural requirement is building an orchestration layer that learns from past task executions without breaking its own foundational logic. The Self-Optimizing Pattern Learning System, or SONA, tracks exact execution trajectories, mapping the specific actions an agent took to achieve a successful outcome. The routing hooks record these positive trajectories and store them permanently as vector embeddings within the reasoning bank for future recall. But continuous machine learning suffers from catastrophic forgetting. As the network forms new pathways to learn a specific codebase, it degrades previously learned foundational logic. Ruflo utilizes elastic weight consolidation, or EWC++, as a strict mathematical safeguard against this data degradation. This diagram demonstrates the EWC++ mechanism. The system applies rigid mathematical penalties to any weight changes that are critical for previously learned tasks, locking that knowledge into place. Agents continuously adapt their logic to map massive, highly specific new codebases, while strictly preserving their core software engineering competencies. System intelligence compounds errively, which requires mathematically locking in past successes so they are never unlearned. Looking at the complete macro architecture diagram, we can observe all 4 pillars operating in unison. A user input payload hits the mixture of experts router, drops into the execution swarm, is coordinated by Byzantine consensus, commits to the RVF storage layer, and loops back to update the network weights via EWC++. Ruflo demonstrates that effective autonomous software engineering requires a distributed operating system, not a chat wrapper. WebAssembly interception bypasses API latency and trivial token costs by keeping simple operations local. Byzantine fault tolerance bypasses multi-agent hallucination by holding errant outputs to mathematical consensus. Elastic weight consolidation bypasses catastrophic forgetting by penalizing the degradation of prior knowledge. The upcoming bottleneck in software engineering is no longer the reasoning capability of foundational models. It is the rigor and efficiency of the orchestration substrates we build to contain them.